So this is a piece of the Clifton Suspension Bridge, iconic bridge in Bristol. 5 years ago now we were asked to inspect this particular part. It's called a chain link and they're part of the chain. The chain's made up of a series of these plates all bolted together. So that's the thing that goes up from the land to the towers, dangles across the Avon Gorge and then across the land the other side. So we developed a way of getting ultrasound through this quite difficult material. It's 150 odd years old, so it's not a modern steel, it's wrought iron, so it's got lots of bits and pieces inside it which aren't particularly great for ultrasound. They scatter the sound, but with our imaging algorithms we were able to produce a high enough resolution image to quite clearly tell if there were cracks of this type. It's quite magic. No one will have ever seen inside that piece of steel ever since it was made. The technology has only just started to exist that can do that, so we were the first to go in there. Fortunately we didn't find anything bad from the bridge's perspective. It all looks healthy. I'm a professor of ultrasonics, so I research all things to do with ultrasound. One of my particular interests is in array imaging, where you've got lots of little sources of ultrasound. We're firing them out into the interior of a structure and we're looking for those reflected signals that come back, and that is very much like how a bat hunts for an insect. It fires out pulses of ultrasound and it looks for those reflections coming back. We're doing the same thing, but because we've got sophisticated equipment, we can capture those signals and form images with them. So this is our system here, starting with an array. So this has got lots of little elements all in this little box, each firing out ultrasonic waves into this aluminium test sample here. That data is then post-processed to form this sort of thing. So this is a classic image of the test structure. We realised that you could take a slightly different approach to forming ultrasonic images of structures, and that would be to capture all the raw data. So that's all the individual time signals, very much like things you'd see on an oscilloscope. And given that there's hundreds of array elements, that's a lot of different transmitter-receiver combinations. That's a lot of data. It's not that much in modern terms, actually, about a megabyte per image, but we capture that and store it, and that information is the entirety of the information that particular array can say about that particular object. You can then take that information and process it to form images, and potentially you can dig down into that data to say other things like, is it a crack, is it an inclusion, what exactly is that feature that you've seen on the image. So that information is buried in that raw data. And so our challenge is well, once we've come up with this kind of concept, our challenge is to use that information to its best effect. This whole area of inspecting structures is critical to the way in which the engineering, those big engineering artifacts that we're so used to seeing work. Yeah, there'd be no planes flying, no power stations operating, no trains running without this inspection regime. Well, the caveat is they could operate, but they'd have to weigh twice as much as what they currently do to build in extra factors of safety. And because we can inspect them and guarantee their safety as they currently are, we have a safe way of operating them. And that's why, although occasionally there are failures and disasters, they're actually incredibly rare. And as each year goes on, they're becoming even more rare. So we're doing this better and better, this idea of inspecting structures. We are getting better at it as human beings.